In this section, we're going to look at the way that non-numeric characters, mostly letters of the alphabet and some other special symbols, can be represented using binary digits. In the early 1960s, it was becoming pretty clear as computing technology was advancing that there had to be a standardized way to represent the characters that we need to read and write in a way that computers could work with, that is to say, to put those characters into binary or 1 and 0 format. And so the American Standard Code for Information Exchange, that is to say the ASCII system, was established so that we could all agree on the way to represent the capital letter E, for example, in binary format. So this chart that you're looking at shows what the hexadecimal and decimal representations are of the characters that we use all the time. These hexadecimal numbers you see are simply hexadecimal forms of the binary representations, and the bold numbers are decimal forms of the binary representations. That's what we're going to look at in this section. The original agreed upon ASCII code represented all printable characters using just 7 bits of data. And since each bit is either a 1 or a 0, that means that there were 2 to the 7th, or 128 possible 7-bit binary numbers. And that means that there was a limitation of 128 agreed upon characters. Now 128 is good enough for most of the English language. That gives us all of our digits 0 through 9. It gives us all of the uppercase letters that we use. It gives us all the lowercase letters that we need. It gives us a whole bunch of mathematical symbols and currency symbols, greater than, less than, a number of punctuation symbols, and some other symbols shown up on here, which are commands for typesetting that we don't usually see in print but are necessary, like paragraph endings or line returns or spaces. But as you can see here, these representations aren't in binary. Instead, they're often given in hex. We already know how to switch between hex and binary, so I've given you a word here that is given in hexadecimal format. Let's convert these hexadecimal representations into text. So first of all, we have the number 55. 55 is a hexadecimal representation. And so if we look up the hex number 55, now notice that we're not going to look at this one. That's not a hexadecimal representation, and we know that because this smaller font uses A's and B's. That tells us that that's the hex representation. On this table, the larger numbers beneath have to be decimal because those simply go up through multiples of 10 like our decimal system does. So 55 in hexadecimal representation becomes a U. 4E is an N. 49 is an I. 43 is a C. 4F is O. 44 is D. And 45 is E. And so that represents the word Unicode. Unicode is related to ASCII. Unicode is a much, much larger coding system. It contains all of the ASCII characters plus many, many more symbols, including symbols that appear in other languages of the world besides just English. So it's a much, much larger, more complex system, but the principles are very similar. So even though it's a fairly old system, the ASCII or Unicode system is still in use. All those characters can be represented in hex, binary, or decimal. So for example, the decimal representations yield the actual characters that they represent when you use them with the Alt key. And the binary forms are ultimately what are used to store that number in memory. So for the example, if you take the word high, H-I, We can see from our little subsection of our chart that using decimal representations, H is the decimal number 72 and I is represented by the decimal number 73. So that means if we go into WordPad or a Notepad or any text editor and enter Alt 0072, it'll give us the letter H, and Alt 0073, it'll give us the letter I. So take a minute and do that now. Open up either a text editor or something like Microsoft Word, and we'll type in, while holding the Alt key, 0072, and we get the letter H, and Alt 0073, and we get the letter I. The text editing feature is turning those numbers from decimal into binary and then representing their binary representations, and that's what we're going to work on next. In the case of 72 base 10, when we convert that to binary, it's equivalent to 01001000 in binary, which is equivalent to 48 in hexadecimal. Now you might look at the binary representation and say, wait a minute, that's 8 bits. That's true, but in the ASCII system, that first digit was always a 0 and was used for error checking, so that's actually not one of the 7 digits that we need. And if we throw away that leading 0, the 7 binary digits that remain make up the ASCII character. So take a minute now with your text editor or Microsoft Word to reveal what the word is that's hidden here. The first thing you should do is to convert each one of these binary representation. Now I've used 8 bits in each of these cases, but you'll notice that the first digit in every one of these 8-bit numbers is a 0, so it's really only the last 7 that are conveying any information here. Convert each one of these into decimal and then type the decimal equivalent of that using the Alt key in Microsoft Word to reveal the message. So just to make sure you're following me here, the first byte of data, 01010100, when converted decimal, becomes 84. The next 8 bits, or the next byte, 01100001, becomes 97. After you've converted all of these into decimal, type them in using Alt 0084, Alt 0097, and so on, and see what word you get. Okay, when you convert the rest of those bytes of data into decimal form, these are all base 10, but I'm not going to write the subscript on all these. We should get 84 and 97 as we did before you did the rest. 114, 97, 100, 105, 100, 100, 108, and 101. Now, let's enter those using a text editor. Alt 0084 yields a capital T. Alt 0097 yields a lowercase a. Alt 0114, the third representation, gives us a lowercase r. And when we're done, you should get the word taradiddle, which is just kind of a slang word for nonsense. Now, of course, when we enter these characters into our computer, the processor almost instantaneously represents the letters that correspond with these numbers. And so making this switch, while we can do this manually, doesn't have to be done manually, of course. And there's lots and lots of websites that will switch between hexadecimal, decimal, and binary representations of these common symbols. Let's take a look at one of them right now. I've copied the entire set of binary data that we have right here. We're going to use an online conversion tool to convert that binary data into text. If you go to unit conversion, that's unit-conversion.info, there's a whole bunch of different converters on this site, but we'll go to Text Tools, Converters, and here we have Convert Text to Binary. Since I'd copied that binary data, I'll now paste it into that box, and we want to change that binary to text. And there's the same conversion we did by hand. Those binary bits of data become the word taradiddle with their ASCII representations. So here's a quick little project I'd like you to do before we wrap this up. Write your name and then convert the characters in your name into hexadecimal form using the table given on page 207 of your text, or you can do a Google search for any similar ASCII table. That is, again, convert your name into hexadecimal representation. Then I'd like you to convert those hexadecimal characters into binary form so that every character corresponds to 1 byte. That is to say, put a 0 in front of your 7 digits so that each character is represented by not 7 but 8 binary places. So rather than my name, I'm going to do the word binary. From the table on page 207 or the ASCII table that we saw earlier in this video or any other one that you can find online, the hexadecimal representations are shown here. Those are straight off of the table. Now remember, to convert those into binary, it's pretty easy. That B should be a 42, sorry. So here are the hex representations. Now switching from hex to binary is pretty easy because remember, every hexadecimal digit corresponds to 4 binary digits. 4 is 0, 1, 0, 0. 2 is 0, 0, 1, 0. So capital B binary is 0, 1, 0, 0, 0, 0, 1, 0. Lowercase I is 69. 6 is 0, 1, 1, 0, while 9 is 1, 0, 0, 1. Lowercase n is 6e, which is, again, 0, 1, 1, 0. E is 1, 1, 1, 0. 61 becomes 0, 1, 1, 0, 0, 0, 0, 1. 72 becomes 0, 1, 1, 1, that's the 7. And the 2 is 0, 0, 1, 0. And a lowercase y is 7, 9, which is 0, 1, 1, 1 for the 7, and 1, 0, 0, 1 for the 9. So at this point, we have the word binary completely stored in terms of 1s and 0s. I'm going to take that data, and we're going to go out to our unit conversion calculator and type in that data and see if it converts the word back for us. And as you can see, all those 1s and 0s do represent the word binary, which is what we started with. So take just a couple of minutes, take your name, convert it into hexadecimal using a table, take those hex numbers, convert it into binary, and then use this same converter to take that binary representation and see if it turns it back into the name that you started with. Okay, while there's more exploring that we could do with the ASCII system and the Unicode system, that probably gets you the idea of how those characters are stored. So you'll have an assignment that corresponds with this. Go ahead and do that. Part of the assignment will be in Blackboard, and there's a separate assignment that you'll get as well. Instructions for that will be given to you shortly. So as always, make sure to let me know if you need help.